We all know data shared between threads needs to be synchronized. But exactly why is that? What makes data inconsistent across threads? Let's dive into the details. For our first example, let's introduce two threads. One changes the value of some variable, the other reads that value. One thing that can go wrong in this scenario is a torn read. Let's assume that A is a 64-bit integer and our process runs on a 32-bit machine which doesn't really support 64-bit ints. This means storing and loading the value might actually consist of two separate machine instructions, both working only on the half of the bits. We don't see it when programming in a high-level language, but that's something the compiler does under the hood. Such situation can lead to one thread loading the value when the other only managed to write half of the bits. Or the storing thread might start writing the new value while the loading one is in the middle of reading it. As you can imagine, this might lead to a giant mess which is almost impossible to debug without going through actual machine instructions. Another way we can run into a data race is called memory reordering. Let's look at a simple example for a single thread first. Naively, you would think that A equals 1 before B equals 0 as it is written. But that might not be true. The compiler is free to reorder memory operations as long as the end result remains the same. If the order of these lines were changed, you would still see the same value being printed out. Why would a compiler do this? Optimizations, for example. If the resulting machine code runs faster, reordering is a simple technique to make that happen. Of course, we can already see this becomes more complicated when we introduce another thread working on the same data. It's totally possible that the assert will fire in the second thread since the memory operations might be reordered in the first one. This is called compile time reordering. There is another form of reordering, runtime reordering, which can be done by the CPU. This is a harder one to wrap your head around, since it can apparently violate causality of events. Let's take a look at a classic example. What would be the value of C and D when both threads complete their execution? 0, 0, 1, 0, 0, 1, 1, 1. In a world with no reordering, the answer would be B, C, or D. But in a real world, all of those answers are correct. How could answer A be correct? From the code, we can see that if one value is 0, the other must be 1, right? Not really. And the answer to this mystery lies in the CPU itself. The processor can execute instructions out of order, and its cores have their own caches. This means any core executing a given thread might see the data as it was at some point in time when it was fetched into its cache, not necessarily its latest value. This effect can also become apparent when storing values. They might be written to the cache and synchronized to RAM at some time in the future. Going back to our example, we can see when such things might happen, resulting in both C and D having the value of 0. As you can see, this makes life very complicated. The results of dealing with unsynchronized data can be apparently indeterministic to the point of being in a state which should not be possible to achieve when looking at the code. That's why in C++ data races can cause undefined behavior. There simply is no way to reason about the state of your data when a race occurs. But from our previous lesson about synchronization primitives, we know we can prevent all those synchronization problems. In the next lesson, we'll see how data synchronization works. Get yourself ready for a tour of memory barriers. But now, hit that subscribe button, leave a comment, and I'll see you in the next one.